So we have been discussing about the photochemical reactions of organic compounds. So today for last lecture we have discussed about the patterno-buchi reaction where carbonyl compounds adds to alkene to give oxetane formation. So we have seen a few examples of patterno-buchi reaction of intermolecular reaction of excited carbonyl with alkene, and also one example as an intramolecular reaction of excited carbonyl to alkene. What we have seen that the excited carbonyl, if carbonyl reacts with unsymmetrical alkene, when carbonyl reacts with unsymmetrical alkene in the presence of light, the excited carbonyl adds to that carbon, which may in turn leads to more stable carbon center radical. There is also possibility that this might react to this carbon to give this radical This is a primary radical, whereas this is a tertiary radical. So we know that the more stable radical is formed and leads to the final product. So the reaction is the selective. The fact that out of the formation of two products, one product is formed. So we get from this we get this product, and from here we get this product. So this is the minor product, this is the major product, and then this is only because of the formation of more stable carbon center radical. So out of this formation of two products in patterno-buchi reaction, when alkene is unsymmetrical, then it gives one of the project images is selective. Another important aspect in this reaction is the stereochemistry, whether the stereochemistry is alkene is retained or it is changed. So that is what this is the topic of interest today. And when we so what I mean to say here is stereochemistry in oxetane formation in patterno-buchi reaction is, say for example, we have a carbonyl. Say for example, say this is pH, and then it adds to cis alkene, CH3 and CH3. This is cis alkene, and then we get a product. We get pH, and now what is the stereochemistry of this in the product? Whether it is the stereochemistry is retained or is going to change. Is retained as a cis, or it's going to change. So that is our interest. So in the same way, if we react this with transalkene, CH3, so if we react this, whether the stereochemistry of product is going to be retained, CH3, pH is going to be retained or is going to change. That is our topic of interest today. And in order to discuss this, we would just like to look at the energy of these this it has been observed that this aspect, the stereochemistry of the retention of stereochemistry of alkene or inversion of stereochemistry of alkene in the oxetane formation, in the product formation, is dependent on the type of substituent, whether in alkene the substituent is electron donating group or is an electron withdrawing group. So this is so the stereochemistry retention or inversion in of stereochemistry of alkene in the product formation is dependent on the type of substituent which is present in the case of alkene, whether is a electron donating or an electron withdrawing group like cyno. So it is very much dependent on this, on the stereochemistry of the product, and hence in order to look into this aspect, we would like to see the energy associated with these alkenes when the alkene is unsubstituted, or so this is the oxetane formation, this is a cis alkene, the stereochemistry of this stereo is going to be, so it is dependent on the energy of the LUMO and homo-LUMO energy of the alkene, whether when it is electron donating CH3, H, or Cn, or when it is unsubstituted. So this is unsubstituted, there is an energy associated with this homo-LUMO, and when this is an electron donating group, electron rich species, there will be some energy associated with this homo-LUMO. So how it is going to be affected when it is electron withdrawing group, how this energy of homo-LUMO of these alkenes, electron deficient alkene, electron rich alkene, is going to be dependent on this. So the stereochemistry is highly affected, is dependent on the what type of alkene and the what type of substituent it is, whether it is an electron donating group or electron withdrawing group present in the alkene. So so this is the matter of interest. See, when we have a carbonyl, when it is alkene reacts with alkene, there is a substituent electron donating groups, such as dimethyl alkene in the presence of light. So stereochemistry is what is the effect of these, and when we have a trans alkene, we have an electron donating group in the trans fashion in the presence of what is the product. As far as the stereochemistry product, we know product is oxetane in all the cases. Now we are interested in the product is same in all the cases. So our interest is the stereochemistry, retention and inversion of stereochemistry in the product. So as we have mentioned that this is when you have an electron withdrawing group, cis alkene, what is the product stereochemistry, and so on and so forth. In order to highlight this, we would like to see the energy of the homo-LUMO of unsubstituted alkene, substituted alkene, and substituted alkene and alkene with the, so this is the unsubstituted alkene, this is the energy of homo and LUMO. So we and then when this alkene is substituted with electron donating group such as dimethyl, when it is substituted with electron withdrawing group such as dicyno, how homo-LUMO is going to be affected with respect to unsubstituted alkene. So since we have an electron donating group like dimethyl alkene, so it is electron rich species, electron dense species, the energy is LUMO position is definitely not going to be same as in the unsubstituted, but it will be slightly higher as compared to unsubstituted. So the LUMO of electron rich species, alkene having electron donating substituent, where the alkene is electron rich, the LUMO is going to be slightly shifted and higher energy as compared to the unsubstituted, and also same as the LUMO in the case of alkene containing electron donating group. And as far as the energy associated with electron withdrawing group is concerned, is electron deficient species. Since there are two electron withdrawing groups are present, is electron deficient, and hence the energy is going to be not exactly same as the unsubstituted, but is slightly, HOMO is going to be slightly lower as compared to the unsubstituted one, and same as the LUMO. So this is the effect is observed when alkene is substituted with electron donating group or electron withdrawing group, as far as the HOMO-LUMO energy of these alkenes are concerned with respect to the unsubstituted alkene. And we are interested in looking into the addition of the carbonyl with the alkene having electron donating group. So definitely the carbonyl on excitation goes to excited singlet state, and then the excited triplet state n pi star, and then goes to excited singlet state, and then triplet state through intersystem crossing. When it's going through intersystem crossing, there is going to be a spin inversion. So this we know that when we have a molecule from the ground state goes to an excited singlet state, and then it comes to triplet state, this through intersystem crossing. The difference between this is the difference between between singlet excitation and triplet excitation. This is a spin unpaired, and this is paired. Whereas this one is going to be paired. So this is the difference. So as far as the when addition of carbon takes place with alkene having electron withdrawing group, since the HOMO is slightly lower than the unsubstituted one, so it has to the carbonyl singlet excited state reacts with the ground state of alkene. So this is an important point to be noted here, that as far as the HOMO and LUMO energy is concerned, with the electron containing alkene having electron donating group, containing alkene electron withdrawing group, the HOMO of electron donating group is slightly higher as compared to HOMO of unsubstituted, as whereas in the case of electron withdrawing group, HOMO is slightly lower than the unsubstituted alkene, and hence when the HOMO of this electron rich species is higher, though the carbonyl triplet state of the carbonyl is going to react with the ground state of the alkene. Whereas when the LUMO is slightly lower, then the singlet state of the carbonyl reacts with the ground state. So this is the difference comes in the as far as the stereochemistry is concerned. This is the important point to be noted, that since in the case of electron rich species, the HOMO is slightly higher than the HOMO of the unsubstituted, the carbonyl, excited carbonyl has to take more time, and it has to come to the triplet state of the carbonyl as to the ground state of the alkene. And so for going for triplet, it has to undergo ring inversion spin inversion to go to triplet through intersystem crossing. Whereas since the LUMO is lower than this, the singlet excited state of the carbonyl adds to the ground state. So this point is very important to note as far as the stereochemistry of the in the product is concerned, whether this stereochemistry is going to be retained or is going to be inverted in the product of the patterno-buchi reaction, that is the oxetane formation. So just to summarize what we have said just now, we have just considered the HOMO-LUMO of unsubstituted alkene, and they said this is the position of HOMO and this is the position of LUMO in unsubstituted alkene. When we have an electron rich species, due to the presence of electron donating group, HOMO is not going to be, say, same as the unsubstituted. Since it's electron rich, is the electron dense species, HOMO is going to be slightly the higher as far as the energy of HOMO is concerned, and same as the LUMO. On the other hand, when we have an electron deficient species due to the presence of a 2 electron withdrawing group, HOMO is definitely not going to be same as the unsubstituted, but it is going to be slightly lower. When the HOMO in the case of electron donating group is higher, the carbonyl triplet state of the carbonyl reacts with the ground state of the carbonyl, and so in order to when the triplet state of the carbonyl acts, when triplet state of the carbonyl acts with the ground state of alkene, carbonyl excited state of the carbonyl has to come to the triplet state through intersystem crossing. There is a spin orientation, and it goes to the spin unpaired states. So triplet state is going to add with the alkene in the electron rich species, whereas in the case of electron deficient species, the excited singlet state of the carbonyl adds to the ground state of the alkene. So this is most important point which is to be noted over here. Now look at the addition reaction. Now this is the carbonyl, this is the cis alkene, is having electron rich species. We have this is the ground state of the carbonyl, this is the ground state of the alkene, and then when the ground excited state, when the carbonyl in the presence of light goes to excited state, excited singlet state, spin is still paired, is excited singlet state. When it goes to the triplet state through intersystem crossing, the spin is unpaired now. Now, as we have seen in the electron rich species, triplet state is going to react with the ground state of alkene because of the higher LUMO energy of the alkene, and hence when it forms the bonding, this will because spin paired will make a bond, so this will make a bond here. Stereochemistry is still going to be same. We have not changing the stereochemistry. It started with cis, going to be here in the cis as well, and also after bonding is also going to be cis in the stereochemistry is going to be retained. Now so in the electron rich species, triplet state of the carbonyl acts to give this intermediate, and now this, in order to form this bonding, the both are spin paired. Spin has to undergo spin flip, and then only it will form the bond, because it has to be paired. One spin up, other fin. So bonding, it has to be in this direction, and it will not form. Bonding will not take place when the spin of the both radicals are in the same orientation. So this will not form a bond to get the final product. This has to undergo a spin flip, and so there are two possibilities that this bond undergo, because this is the double bond character. The ring rotation of the double bond is restricted. Now it is a single bond, and there is a free rotation is possible, so it will undergo ring inversion, and then when it goes to spin inversion, and then so there are two parts. Ring it will undergo bond rotation. So when bond rotation takes place, then it will the stereochemistry is going to be changed. Now when bond is going to change, now the cis the methyl group now goes to the opposite direction, and hence, but still spin is not changed. Spin remains the same. Spin orientation, spin of the radical remains the same, only bond flip rotation takes place, and when bond rotation takes place, methyl group goes other side, and now the stereochemistry is going to, now it was cis initially, now it has become trans. When it is now it will undergo a spin inversion, this is spin flip inversion, and then it will take a bond to give this product. So where now it is going to be a trans. So this is the important step where there are two possibilities here. First, it will undergo a spin flip. It will undergo a spin flip to form get the both the spins in opposite direction, so that bonding takes place, or it will undergo bond rotation. So there is a competition between two pathways, path A and path B. Path A is the spin flip to go to the spin orientation, and then then it forms the bond. Where the other possibility is bond rotation to change the stereochemistry, and then spin flip, and then get the product. So it has been found that out of these two pathways, the bond rotation is much faster. Bond rotation much faster than the spin flip. It has to, so that's why this route is favored, and it goes to first bond rotation, change in stereochemistry, then spin flip, and then to form the bond to get the stereochemistry. So what we have seen that in the case of electron-rich species, in electron-rich alkene, in the cis orientation, in the product it's going to be a trans, because of the reaction of the excited triplet state of the carbonyl with the excited ground state of alkene. And to get this intermediate out, there are two pathways open here. One is spin flip and then bond formation, or bond rotation and then spin flip. And it has been found that bond rotation is much faster than the spin flip. So before it goes to spin flip, to go to the other orientation of the spin, it undergoes bond rotation, change in stereochemistry, then spin flip, and then form. So cis alkene on reaction with carbonyl in electron-rich species, there is a change in stereochemistry. From cis goes to trans in the case of electron-rich species. Whereas on the other hand, whereas in the when we have an electron withdrawing group, when we have an electron, what we call it as let us wipe it out and see. When we have an electron-rich species, so when we have an electron-rich species, such as the cyno group here, then we have a cyno group Cn, electron deficient species such as cyno-electron withdrawing group, this electron singlet state, because the HOMO of electron deficient species is lower than as compared to unsubstituted. So the excited singlet state of the carbonyl acts with the ground state, and hence there need not to be any spin flip, and because the both bonding is possible in the case of electron. So and hence the stereochemistry is going to be retained in the case of electron withdrawing substitution. So just to summarize what we have said, that in the case of electron donating group such as dimethyl, in the case cis goes to trans in the product formation, because it undergoes bond rotation followed by spin flip. Triplet state of the carbonyl adds to the ground state of the alkene to give the product in the the change in the stereochemistry from cis to trans. So from cis it goes to trans in the case of the electron-rich species, and same as the trans electron-rich species such as dimethyl trans goes to cis in the case of in the case, I mean the product formation. On the other hand, when we have an electron withdrawing group such as dicyano, the excited triplet state of the carbonyl adds to the ground state of the carbonyl, so there need not to be any spin flip. Both the bond formation takes place and stereochemistry is going to be retained in the electron withdrawal. Cis gives cis, trans gives trans in the case of electron withdrawing group, whereas cis gives trans, trans gives cis in the case of electron donating group and electron withdrawing group. So there is a change in stereochemistry in electron donating group. There is a change, there is a retention in stereochemistry in electron withdrawing group. This is because of the fact that electron rich species LUMO is higher, and hence because of the higher LUMO position, the carbonyl has to undergo goes to the triplet form of the carbonyl reacts with this, and in order to go to triplet form it has to undergo intersystem crossing, spin flip, and then goes to the first bond formation takes place, and then after the bond formation takes place the bond rotation is much faster as compared, and then it goes to the first bond rotation. Stereochemistry is going to be changed. Now it was cis goes to trans now, and then it goes to spin flip and then bond formation to give this inversion is stereochemistry. On the other hand, when we have an electron withdrawing group such as the ground state reacts with the excited singlet state, and hence it need not to undergo spin flip to gives the change in the stereochemistry. So this is the overall conclusion as far as the stereochemistry in the product formation of oxetane formation takes place. The stereochemistry in electron donating group remains goes to inward change in stereochemistry, the retention in stereochemistry in the product in the electron withdrawing group. So this is the and why there is this thing happening. This is because of the fact that the one form adds to other form in the reaction taking place. This is because of the position of homo-LUMO in the case of electron rich and electron deficient species, and hence the ground state of the alkene in both the cases. Ground state of alkene reacts with the excited state of the carbonyl. The difference is in the electron rich species triplet excited state of carbonyl reacts, and for going for the triplet it has to undergo a spin flip through intersystem crossing, and then it first form the one bond, and for second bond, since the double bond character is lost, it's a bond rotation and then spin flip, then going to form goes to spin and then form the product. So this is the story regarding the stereochemistry of alkene is concerned. So we stop here as far as the stereochemistry of the is concerned. Thank you very much.